Welcome to this SAS Explore talk. The title of this talk is called An Aircraft Landing Problem, an Optimization Solution. We're going to talk a little bit about the aircraft landing problem itself, as well as the procedure inside of SAS Viya, the op model procedure, that we're going to use to solve it. Let's take a step back for a moment. Why would we need to use optimization at an airport? Well, the reality is there are a lot of things that can go wrong. If you've ever been stuck in an airport for any travel-related unexpected events, you know exactly what I'm talking about. And airports look at things in one of two buckets: things they can control and things they can't control. Of course, the one thing that they can't control is the weather. That changes often, and that involves a lot of slowdowns and bottlenecks that, frankly, are unavoidable. But if they can control it, they oftentimes very much want to. And that's where optimization can play a key role, especially when we talk about the takeoff and landing of aircraft to and from a particular airport. One of the biggest bottlenecks at commercial service airports are the number of runways available for takeoffs and landings. For example, Heathrow in London, one of the busiest airports in the entire world, only has 2 runways. Same thing for LaGuardia, just outside of New York City. One of the largest airports in the United States, if not the world, in terms of overall traffic in and out of that airport, and they only have 2 runways. So you can imagine using those runways inefficiently only results in a cascading of problems in terms of delays, cancellations, so on and so forth. So airport managers and people who work in the airline industry very much want to make the most efficient use out of the resources that they have. And third bullet point, it says the efficient runway usage is essential for consistently ensuring safe and on-time passenger travel. Exactly. And so if an airport can control it, it wants to look for ways to control it as efficiently as possible to ensure safe and on-time passenger travel. What the aircraft landing problem focuses on specifically is on inbound flights, landing. But this problem could be easily extended to cover both in and outbound flights as well. Let's take a moment and see what exactly does the aircraft landing problem do. Let's take a small example. Let's say we have an airport that has 2 runways, and we have 7 aircraft that are looking to land at that airport on one of the 2 runways. And each one of the aircraft, they have desired landing times in which they want to land. For example, the aircraft 1 wants to land at 10:15, aircraft 2 wants to land at 10:12, so on and so forth. Given this information, the aircraft landing problem assigns each airplane to a runway, and then it sequences the landing order of each runway so that all airplanes land as close to their designated landing time as possible. So let's take a look at how this small example might play out when we run the aircraft landing problem. Well, for runway number 1, aircraft number 1 that wants to land at 10:15 could be assigned to runway 1 to land as close to 10:15 as possible, followed by aircraft 5 to land directly after aircraft 1 at as close to 10:20 as possible, followed by aircraft 7, which again wants to land as close to 10:24 a.m. as possible. On the second runway, aircraft 2 wants to land as close to 10:12 a.m. as possible, followed by aircraft 4, followed by aircraft 6, and last but not least, followed by aircraft 3, which wants to land as close to 10:25 as possible. This would be one example of what the aircraft landing problem gives us. For each runway, it says this is the order of the aircraft that are going to land, as well as what are the exact times in which they can land. One thing that we have to be cognizant of, and one thing the aircraft landing problem has to take into account, are separation criteria. So let's take an extreme example. Let's say we have two aircraft that both want to land at, let's say, 10:12 a.m. We could let one aircraft land at 10:12 and 10 seconds, followed directly by another landing at 10:12 and 25 seconds. But is that safe? Probably not, right? And so there's this inherent separation criteria that the model has to adhere to. The ALP incorporates this separation criteria primarily to ensure safe and adequate time between consecutive landings on the same runway. Now, the FFA gives guidelines and certain specifications for what those separation criteria are, depending on the size of the airplane, turbulence, and things like that. What the aircraft landing problem does is we ingest those as parameters to be used to ensure that if there's a 5-minute separation criteria, for example, between aircraft 1 and aircraft 5, that our recommendations from the model adhere to those separation criteria. So how do we take those into account in the model? Well, we read in effectively an n-by-n adjacency matrix for accommodating the separation criteria between plane I and plane J. Now, of course, that's only the case when plane I lands before plane J on the same runway. So, for example, taking a look at airplane 1, if airplane 1 lands on runway 1 at 10:15, and airplane 5 wants to land directly after it, well, row A1, column A5 gives us 4 minutes. And so there has to be a 4-minute separation window between A1 and A5 if plane A1 lands before plane A5 on the same runway. So the way that I like to think about this separation time matrix, and the way I like to interpret the elements inside of this matrix are, it's the minimum amount of time that plane J must wait before landing if scheduled to land directly after plane I on the same runway. So let's take, for example, plane A1 and A5. If plane A1 lands exactly on its target landing time of 10:15, well, row A1, column A5, we have to wait 4 minutes before plane A5 can land. As is, does that respect the separation time? Yeah, it does. Plane A1 can land at 10:15, and as long as plane A5 lands at 10:19 or later, that separation criteria is upheld. And so we can assign these landing times of exactly 10:15 and exactly 10:20. Well, what about between planes A5 and A7? Well, row A5, column A7 is also 4 minutes. And we can see if plane A5 lands at 10:20, plane A7 therefore can land at 10:24. And we play the same game down below. If plane A2 lands at 10:12, what's the separation criteria between planes A2 and A4? Well, row A2, column A4 is 5 minutes. So if plane A2 lands at 10:12 plus 5 minutes is 10:17, well, then plane A4 can land at 10:18. Followed by A4 and A6 for 3 minutes, followed by A6 and A3 for 3 minutes. And so in this example, this is a special case, not really a special case, but this is really the best case scenario where in this example, based on the separation time, every plane can land exactly on its desired landing time. Plane A1 landed exactly at 10:15 when it wanted to. Plane A5 landed exactly at 10:20 when it wanted to, so on and so forth. Is that always the case? No. But how can we let the optimization model determine that for us? So when we think about constructing this optimization model, there are a few additional considerations that we need to think about. The first is, well, what if each plane doesn't land exactly on their target landing time, right? What we just saw was a perfect case scenario where every plane did land exactly on their desired landing time. But when that's not the case, a per minute penalty is applied to each plane if they land before or after their target landing time. Now, let me ask you, would you rather land a minute early or a minute late? I think universally we would all say, well, if we're going to miss, let's land earlier rather than later, right? And this model accommodates that. So landing later is penalized heavier than landing earlier. Next, the objective function minimizes the total penalty across all planes. So the example we saw a moment ago, the overall objective function value would be 0 because every plane landed exactly on their target time. But when that's not the case, we want them to land in such a way so that each plane is assigned to one runway. The separation criteria is upheld, and that objective value, or rather the total penalty across all planes, is as small as possible. Now, again, a few other kind of common sense constraints, but things that we'll have to build into the model, is that each plane can land on only one runway. In our case, either runway 1 or runway 2. Next, if planes I and J land on the same runway, well, we know that the separation criteria will have to be upheld, but also either plane I lands before plane J or plane J lands before plane I. This ensures that the plane only lands once. And so these are other things that we'll have to accommodate in the model. So how do we do this in SAS? Well, we can use the opmodel procedure or the run opmodel action in SAS Viya to build this mathematical model from the ground up. We'll define the parameters, we'll define the decision variables, we'll define the objective, the constraints, so on and so forth, and solve this model directly inside of the opmodel procedure. The opmodel procedure itself accommodates several different types of solvers. The black box optimization solver, constraint programming, conic optimization, and then some of the more traditional linear programming, mixed integer linear programming, various types of network algorithms, general nonlinear programming, and quadratic programming solvers. For the aircraft landing problem, we're going to use the mixed integer linear programming solver. Okay, so enough talking, enough of the slides. Let's go and jump into a demo and see how we build and solve the aircraft landing problem inside of Proc Opmodel. All right, I'm inside SAS Studio now, and I'll start up a CAS session that I'll call MySesh. Down below, I'll create a live name that I'll call MyCAS, and I'm going to use the IML action set, which is short for Interactive Matrix Language, to simulate the data sets that we're going to use inside of Proc Opmodel. IML is a great action set. I don't have time to talk about it here today, but I encourage you to take a look at it, especially for different types of numerical analysis, working with matrices, or in our case, simulating data. So inside of ProcCAS, I'm going to come down, I'm going to load the IML action set, and we're going to use 30 planes. And so I'm going to simulate 30 planes along with their respective separation criteria. And I'm going to create 2 output data sets, or CAS tables, that we're then going to read into Proc Opmodel. Let me go and run this simulation code. And let me print these tables to the results viewer. So this first table, mycas.landing_schedule, I simulated 30 planes. and so I have 30 observations in this table. I've got a unique identifier for each plane, A1, A2, all the way to A30. And I've got various parameters that I'm going to read into ProcOptModel. The first one corresponds to the earliest possible landing time for airplane 1. T corresponds to the target time. So plane A1 wants to land at 11:46. It can land as early as 11:31, but no later, and that's the third parameter L, no later than 12:01. G and H correspond to the individual penalty for landing 1 minute early or 1 minute late. So for example, G, we're penalizing each minute landed early by 0.25. So if you land 2 minutes early, that's a penalty of 0.5. Compared to H, which is a penalty for landing late. If you land 2 minutes late, you're penalized by 2 instead of 0.5. And so again, G and H are user defined. You can toggle and weight these however you would like to. But this is the structure for the landing schedule table that we'll read into ProcOptModel. Scrolling down, we'll take a look at the separation criteria. I've got columns from and to corresponding to I and J from that separation time matrix we saw a moment ago, along with the amount of time, in this case in seconds, for the separation criteria required between plane I and plane J. So for example, if plane A1 lands before A2 on the same runway, that separation time corresponds to 240 seconds, or practically 4 minutes. So those are the two tables. Coming down into ProcOptModel, the first thing I need to do is to declare the 3 different sets that we'll use. I'm going to have a set of planes, 30 of them. I'm going to have a set of arcs corresponding to the from and to table here. And I'm going to have a set of runways. And in this case, I'm going to have 2 runways. I'll have runway 1 and runway 2. Coming down further, I'll define the parameters indexed by the appropriate set. And so I'll create a parameter called E, which, you guessed it, corresponds to the earliest time for each plane that it can land. L corresponds to the latest possible landing time. T is the target, so T is the target landing time for each plane. G and H are those unit costs for landing early and late. And then last but not least, S corresponds to that separation time required between the 2 planes. So once I've declared these sets and parameters, the read data statements down below read in the separation times and the landing schedule table into ProcOptModel and populate those sets and parameters accordingly. So once we've got the data set up and read in, now for the fun part, let's build the model. Down below, I'll use the var statement to declare my decision variables. My first decision variable X for each plane corresponds to the actual landing time, right? Each plane has its own target landing time. Here, we're going to let the model determine what the actual landing time is, and hopefully the actual landing time is exactly what that target landing time is, or as close as possible to it. Down below, alpha and beta. Alpha corresponds to how many minutes early did that particular plane land. Beta corresponds to how many minutes late did the actual, or did that plane land. Then down below, Y and theta are binary decision variables. Y corresponds to did plane P land on runway R, yes or no? So for example, did plane A1 land on runway 1, yes or no? Did plane A1 land on runway 2, yes or no? Down below, the last set of decision variables, theta, we'll have 1 theta for each arc and runway combination, and that will be binary as well. And the way that we can interpret theta is, did plane I land before plane J on runway R, yes or no? Coming down, we'll specify the objective function, which we want to minimize the total landing cost. So we're going to sum across all planes the penalty for landing early times the number of minutes that we landed early, plus the penalty for landing late times how many minutes late that particular plane landed. And as you can imagine, if a plane lands exactly on its target time, alpha and beta will equal 0. And if every plane lands exactly on their target time, then the entire objective function will equal 0. Down below, we define the constraints. And the first constraint says that each plane has to land on one and only one runway. Coming down to the runway definitions, here this defines the relationship between theta and y. So for example, if planes I and j land on the same runway, then either theta ijr or theta jir has to equal 1. Since either plane I lands before plane j on runway r, or plane j lands before plane I on runway r. So when both planes land on the same runway, y sub I comma r and y sub j comma r will both equal 1 for the runway in which they are both scheduled to land. So subtracting by 1 here on the right-hand side ensures that this particular inequality holds. Down below, we have a few other runway definitions that further define this relationship between theta and y. And for folks that really want to get into the details of the aircraft landing problem, I encourage you, there's also an attachment that goes into the code in a lot more detail. And so it explains each line of this line by line and really explains the logic between how and why these constraints are constructed the way that they are. And so again, for folks who want a little bit deeper of a dive into this problem, and for that matter, into the op model procedure itself, I encourage you to take a look at the handout that's associated with this talk. Down below, we define some further constraints. Once the model is built, I'll specify the solve statement. What that does is that ingests the parameters, the decision variables, the objective function, the constraints, and determines what the most appropriate solver to use is. On one of the slides earlier, we showed all the different types of solvers that are available inside a proc op model: linear programming, mixed integer, nonlinear, so on and so forth. And the solve statement will determine for us what the most appropriate solver to use is. It'll call and then use and solve the model above. Down below, I use a concurrent for loop, which most for loops run sequentially, right? So if you specify for each instance, it'll run 1, then 2, then 3, then 4, so on and so forth. What the co-for loop does is it instead runs those concurrently. And so it operates and it executes much faster than traditional for loops. Down below, once the model's ran, I want to create an output data set. And so I'll specify the create data statement. I'll create an output CAS table called myCAS.landing_times. And I'll bring in the earliest, the latest time, the target time, and then the actual landing time solved for by the model. And I'll call that column actual, and I'm setting that equal to the set of X decision variables that I specified earlier in the model. And then for each one of the runways, I'll have a column for each one of the runways showing those binary assignments for each plane. So let's go and run this. Let's go and run from proc op model all the way through to quit and take a look at what those optimal assignments are. Now, of course, we know if every single plane lands exactly on its target time, then the objective function will equal 0. Let's see if we get an objective function equal to 0 or not. I can come down and take a look at the solution summary. I can see that the solver called was the mixed integer linear programming solver. The algorithm was the branch and cut algorithm. The objective function was landing cost, which I defined above. The solution status is optimal with an objective value of 75. Pretty close to 0, but what that tells me, because that's a non-zero objective value, it tells me that at least one plane had to land at a time other than its target time, because then it had a non-zero penalty value that was applied. Let's come down here and take a look. What I'll do is I'll just print this landing underscore times table to the results viewer. So this is what the output table looks like. We have 30 rows, one for each plane. So we have the unique plane identifier in the plane column. We have the earliest, latest, and target times, which were just parameters that we passed through and used in the construction of the optimization model. This actual column corresponds to those X decision variables that the model solved for. And so we can see for plane A1, it wanted to land at 1146. And it did land at 1146 on runway 2. We can come down to plane A5. It wanted to land at 1118. It is landing at 1118 on runway 2, so on and so forth. But because we had a non-zero objective, we know that some planes didn't land exactly on their target times. One of those planes is plane A17. Notice that it wanted to land at 1103, but it's instead landing 1 minute early at 1102. Also, we can take a look at plane A8. It wanted to land at 1128, but is forced to land 2 minutes early at 1126, in this case on runway 1. And last but not least is plane A26. Row 15, it wanted to land at 12:13, but it has to land 2 minutes early at 12:11. You can think about trying to do something like this manually, and it being, at worst, a long, drawn-out, arduous process, or at worst, a full-on exercise in futility. But the op model procedure makes it very easy to build and construct optimization models of varying scale and complexity. And so hopefully you've enjoyed this example walking through the aircraft landing problem. And if you're new to ProcOp model, I encourage you to look at the various types of functionality available to you. It's a very powerful procedure that again allows you to build and solve various types of optimization problems. Thank you guys for coming to this talk. And if you haven't already, please take a look at this handout, which, again, if you want more detail, goes into detail of the op model procedure, a little bit of the syntax as well, along as well as the construction of the aircraft landing problem. Thanks.